right, and we're back again to talk more about stars. Before we start getting into all the other different mechanics of the different sizes of stars, we're going to do a little quick work on just some of the terminology that we're going to be using in the stars. And this is a great picture. It's not the angle you're used to seeing it, but it happens to be Orion, the constellation Orion. And so we've got his belt is over here. Rigel, Betelgeuse, it's on its side. His sword is down here. The M42 and 43 are right here. Those are known to most people as the Great Orion Nebula. And then right here, it's very hard to see, but right in that area right there, this is the Flame Nebula, but the little Horsehead Nebula is right there on the far, that would be the eastern side of Orion's belt. All right, so properties of stars. So some of the terminology that we need to kind of be clear about as we move our way into stars and then onwards into the galaxy and the universe. So we're going to be talking about luminosity and temperature and masses because they're kind of all interrelated. So when we talk about luminosities, we're talking about the output of a star. When we talk about the brightness, we're going to have to deal with both how much the star is putting out in light and the distance, how far away it is. All right, so one way to think about that is kind of this little triangle. So the star is actually putting out X amount of light. It's generating it at its core. The distance away from us that star is changes the observed brightness. The lower the luminosity, the observed brightness is different. Two stars of the same brightness at different distances, two stars with the same luminosity at different distances will have different observed brightnesses. So if you can kind of remember these three parts of the triangle, if one of them is changing, something else is going to change. So you will hear people talk about apparent brightness, and that is the amount of light that we actually get to see that actually reaches the Earth. Luminosity, again, is actually what's being created. All right, so a little bit of a thought question. I'm going to take you through a couple of steps to get to that. So, Alpha Centauri. So our closest star is actually a binary, Alpha and Proxima Centauri. And so Alpha Centauri and the Sun have about the same luminosity, right? So they are generating the same amount of light. So which one actually appears brighter to you? Right? Which one is actually do we receive more light from here on Earth? All right, so I know you have an answer in your head, but again, just a reminder, the Sun is only 8 light minutes from Earth, and Alpha and Proxima Centauri are 4.4 light years away from Earth, so there's a distance issue in here. But even if there wasn't a distance issue, you should be able to figure out that there is a distance issue because we know how bright the Sun is. The Sun is bright enough that when we are on the side of Earth that is facing the Sun, we cannot see any other stars in the sky, right? Because the Sun is overpowering everything. Now, if we had exactly the same instance with Alpha Centauri, that meant that any time that we had that star anywhere close to our visible horizon, it too would be overpowering. So here's our little miners. It's an example. Each one of their helmets has exactly the same luminosity. The bulb is exactly the same. The battery is brand new. So they're all putting out exactly the same amount of light. Although we can tell by looking at them, since we know the light is the same, we know that distance has to be an issue because this guy right here with the B helmet and E are completely different. All right. So that takes us back again to kind of the inverse square law for light. We saw this with gravity and distance. We're seeing it again now with light. So as we increase the distance, the area that light has to cover is going to increase. So because it's an inverse square, it's one of those, if you double the distance, right, that the light will now be 4 times weaker. All right. So when we take a look at all of our stars and we can compare them by luminosity, we tend to use the sun as a measurement. The same way we use the distance between the Earth and the sun, called an astronomical unit, when we're talking about things in our solar system. When we're talking about other stars, the easiest thing for us to do is to measure it against the star we know the best, the sun. And so when we're looking at those stars, that's what this L sun means. It's the luminosity of the sun. So when we're talking about the sun itself, it's just one solar luminosity. And so that's kind of how to read these kind of facts on the different types of stars. All right, so we're looking again back here at Orion, and then how do we figure out how far away these are? Well, we have to be able to figure out something else about the star, right? We've got a triangle, so we're trying to find distance. We need to have a luminosity or an observed brightness. All right. So one piece that helps us determine distance, if we wanted to, was to figure out parallax. And we talked about this at the very beginning of the course. And it was one of the things that kind of stymied early astronomers, and that they understood what parallax is. And we did the experiment where you hold your thumb out and you blink left and right, and you can see the jump, and so that you know that the thumb is closer to you than the objects that are in the distance. And they could see how if the Earth was orbiting the sun, we should be able to see that, because that's like a giant face with eyes on opposite sides of the sun. And since they could not determine or could not measure that level of parallax, therefore it could not be there. So it was one of the things that kept the Earth in the center of our solar system for a very long time. So with stars, it was very, very kind of hard to measure. It took being able to measure very, very small motions to fix that. So I'm going to jump out real quick, and I'm going to show you this little demonstration. And you have a similar demonstration in the module as well. So let me get over there and we'll do that. And we have our sun and we have the Earth, and the Earth is going to orbit the sun, and so we kind of have these particular angles. So what we have right here is we've chosen a star that is the star that we're going to kind of look beyond. It is our thumb, right, in the parallax example. And we're looking at this set of background stars, and we're trying to measure any movement of those stars in the background. So here is our foreground star. It's the blue one right here. All right. And so as we set this in motion, go ahead and watch different things that we're looking at. So first of all, watch right here, and we're looking for this angle of motion to get. Once we get the angle that we have right here, we can figure out the distance. So I'm going to unpause time, and you can see the foreground star moving against the background stars. And so that motion from left to right, the base of this angle, is what we need to try and calculate the distance. Okay, so just as an example of why it was tough, we're going to run it again. And we're going to look at this with just a home telescope. And if you watch the blue dot, you cannot see motion. So it's not surprising that the folks that didn't have telescopes could not see motion either. When we jump out to a space telescope that has much, much better resolution and has more stars to measure, then you get a very different answer. Okay, and so that's how we can get the base of that triangle and calculate then kind of the distance. So here is another example, and the reason why I wanted to show this one is that there's a picture of the stars here, and then another picture of the stars 6 months later. So when people were originally calculating these distances, this is what they had to work with. I want you to imagine these as two glass plates, and working in a very, very small room with just natural light and a stand with a mirror behind it, and you would have to flick back and forth between these two images to figure out which ones were moving. And just looking at it, it's kind of tough. I mean, you can eventually pick out the motion, but you have to go back, forth, back, forth. You have to make them blink. And they didn't have computers to do this when they were first working on them. They were physically using glass photographic plates and layering them on top of each other and matching all of the stars in the image and looking for the stars that were moving. Okay, so that parallax and distance. So this is the actual formula that we're using to calculate those what that the arc second, so the angle of the movement of those stars in space, and so therefore the distance, the eventual distance in space. Now, we did this activity early on when we were talking about constellations and asterism, so you guys have a very good idea that when you look at the constellation Orion, you know those stars are not the same distance apart anymore. So you know that each one of those stars is a very different distance. You actually got to map it out with Ursa Minor. All right, so another set of terminologies that we're going to work through, very, very similar to what we've just been talking about, is how much the star is actually producing in light. Um, so if we have two cars that are identical, so everything, the power and everything is done to the light, just like the miners' helmets, right? We can use those two to help us identify the distance between them because if one is brighter, it's closer. Um, Now, if we have two stars and then they are the same distance, but one is brighter, and we know the distance is the same, then we must know that the one is brighter is actually producing more light, right? So the absolute magnitude of something, and magnitude is a word we haven't used yet, and it's another type of word for brightness. It's going to mean something just a little bit different. But the absolute magnitude is if we had our stars all at the same distances, right? Then we can see the intrinsic, we can see the difference in the power of the stars all together. So that absolute magnitude is put everything at 10 parsecs away, and then you would be able to see the absolute power difference between the two. So absolute magnitude. We use the magnitude scale. It's the oldest scale we have for judging the brightness of stars. And it's, I mean, we've used this term outside of astronomy, you know, the magnitude of an issue or the problem. When you go out and you start to watch the sunset and the first stars come out, the ancient astronomers called those our first magnitude stars. They were the brightest ones. They were the ones that overcame the power of the sun first. So you think about those types of stars, you know, Venus is very, very bright. It had a much higher magnitude than the first magnitude stars. So the first magnitude stars came out first, then the ones that were slightly dimmer would come out second, so they were second magnitude, and then the ones that were a little bit dimmer came out third, and they were third magnitude. So then if you had something brighter than the first magnitude stars, you were stuck because you already started using increasing magnitude for fainter objects. So you have on a magnitude scale, you've got negative numbers. So the negative numbers are higher. So in this case, the sun at about negative 26 apparent magnitude, the full moon right about negative 12, Venus at about a negative 4, and then something like Vega is at absolute 0. And so you've kind of got all of these different magnitudes. And then here's a more detailed list of those magnitudes. So this one's from your book. All right. So we have a whole different issue. So we've got all these different issues we have to deal with. We've got trying to figure out distances by using the light, but then we have to understand the star and how it's producing light to actually know what the luminosity is of the star and or what the observed brightness of the star. So knowing how hot they are is going to kind of help us determine that. Right, so temperatures of an object, and we talked a little bit about this when we were talking about light in general, but um, every object as it heats up emits that thermal radiation, and the hotter it gets, the more it is going to release. So you stick a hot metal stick in a fire, you watch a blacksmith do this, it starts off as black, and as it warms up it starts getting red and then orange and then yellow, and then it moves all the way up to white hot. And so that change in color through the spectrum tells us about the temperature of an object. So a blacksmith can look at a piece of metal and what color it is and know the approximate temperature of that piece of metal. So for example, too, you have a light bulb, and as you increase, right, the energy going into the light bulb, it's going to glow brighter and brighter. So again, temperature increases result in a higher luminosity. So that's going to work with stars too. So now how can we apply that to stars and look at stars and talk about that? So remember how I talked about the people that would actually take the glass plates of stars. So these are again spectra. Oops, wrong way. So these are different spectra from different stars. And if you look across the lines, you'll notice that as we get towards the bottom of this list, we have a whole lot more lines. However, we see a similar lines moving across all of the spectra. So what happened is people were classifying stars, and actually it was a team of women at Harvard, and they were all hired as computers. They were probably the lowest paid people at Harvard at the time, but they went through boxes and boxes and boxes and thousands of glass plates of the spectra of stars, and they were trying to help classify stars. And so they went through several different renditions, and they finally realized that these spectral lines told you something about the temperature. The hotter an object was, and if you go back and think about the solar nebula and when things would condense out, if it's too hot, right, all of the molecules cannot condense. They can't even form into their atoms if it's too hot. But once it cools off enough, they can, the atoms can form and then the molecules can form. So looking at these top spectra, it is so hot, things have ionized out, right? There's just not the material there to make very strong lines except for here in the hydrogen. And then as these stars start to cool, you start picking up all of the different molecules that are and other atoms that are in the stars, because they have a chance to kind of condense out. So they determined that they could organize and rank stars based on temperature. And so the letters were previously assigned, and they ended up rearranging them: O, B, A, F, G, K, and M. And one way to remember that, oops, it's not there, so I'll just do it for you. All right, let me just get back. Is "Oh, be a fine girl, kiss me." All right, so that's how you remember the stars in order. And we're going to see some pictures of the women that did this. All right, so again, thermal radiation, hotter objects emit more light at all frequencies, and the light emitted as photons comes off at higher energies. And again, this is just remembering all of those phases. As we increase the kinetic energy or the temperature of an object, we move through and we change this actual phase state of the gas that is there in a star. All right, so "Oh, be a fine girl, kiss me" alternately. Only boys accepting feminism get kissed meaningfully, or a third one that's not there is knowing mnemonics. All right, so thinking about that, "Oh, be a fine girl, kiss me," which of these stars is the hottest? "Oh, be a fine girl, kiss me." All right? Yes. The A star is going to be hotter than the other choices. So here are the women that did this. So Annie Jump Cannon is well known by name, but there were so many women that went through the Harvard computers. We'll get to talk to some of them a little bit later on as we get into more and more about our stars, Henrietta Leavitt, and others as well. So just really very, very, very important people in the history of learning about stars. Okay, so with that, we can now take a look at these different stars, and by using color associated with them, help determine the actual temperature of output. So these hottest stars, we have 50,000 Kelvin, the coolest ones 3,000 Kelvin. Remember, our sun's right around 6,000 Kelvin. All right, so then how do we measure the masses? Because if we know the temperature and we know the mass, we can figure out the overall output of a star. And remember, we talked about both asteroids and Jupiter. It's really handy if you have two things orbiting each other, because with an orbit you can help determine the mass. So the nice thing about stars is they are more likely, they're just as likely to be in groups as they are to be single. So our sun is a single star, but that's not how most stars are. So if you can get two stars that are orbiting each other, then you have a path to mass. So we look for binary stars. And so we can look at them based on the amount of light that this star is putting out and this star is putting out, and as they pass in front of each other, or behind each other, how that changes. So here they are side by side. We get a single output. As B star passes in front of A star, we continue to see B, but it's blocking out part of A, and then again side by side, so we see both light, and then now B is completely blocked, right? So that kind of starts to give us a period. We can map that out over time. And that's going to help us understand what's going on with the gravity and then also with the mass. So the different types of binary stars that we see kind of really is dependent upon how we detect them, visually, spectrographically, or as an eclipsing unit. So the visual binaries are the ones we just talked about. We actually see them orbiting each other. The spectrographic binaries, we actually see the motion of both stars as they move towards and away from us, because even though B is orbiting A, the mass of B and A are interacting with each other, so it's still tugging at A. So A is going to move along with B as well, so we can kind of measure both of those. And then we just showed you an example of that eclipsing binary. So once we do this, we're right back again at with Newton and Newton's version of Kepler's law, and using mass and distance to come up, or using, in this case, the period and the distance between the two objects to come up with a mass. All right, so once we can get two of those, we can end up with the third. All right, so that's a little bit about some of the technical aspects of looking at the stars. And then we've got one more little segment on this as well, as we get into kind of more details of how we group stars together.